in practical terms, the regular schedule would have had the presentation from the colleague of Cyper. Given the delay and given the practical things with the catering, I would suggest that we take our break now, slightly truncated, rather than 60 minutes, we take, let's say, 40, 45 minutes, and then we resume the presentation from the side of Cyper. Apologies for this delay, but I think it's the best compromise at this point. Okay. So for the people on remote, we'll be offline for 40, 45 minutes, and then we'll resume with the presentation from the side of Cyper, okay? So welcome back. We get back to our regular program with a presentation from the side of Semidynamics. And this is, I think, a presentation that kind of meshes well with the prior one that we had. The presenter is Mr. Jose Maria Arnau. He's a senior hardware engineer. He leads the activities around vector unit creation and validation. As you know, Semidynamics has been providing the core, the processing core for the PI series of projects. During the projects, we have had 2 generations of the scalar core, Avispado and Atrevido, and this is interfaced with a vector unit that is being created within the project. Among other IPs, Semidynamics also now has options for the vector processing part, and Jose Maria is very active in that line of work.
So we are all set? Yes, thank you very much. Thanks, Manolis, for the introduction. Let me talk a bit about Semidynamics first. We are a company from Barcelona, but we also have people in Germany, in Asia, and in the US. We have over 150 employees right now, and we are in the IP business. We sell IP for AI. We have been around for 9 years. So what have we done during these 9 years? This is our IP portfolio. We have Atrevido, a RISC-V out-of-order core, Gazillion Mises, our technology to hide the memory latency, a vector unit fully compliant with RBB 1.0, a tensor unit that implements our custom matrix extension, and Cervell, an NPU that combines all our IP. So let's go one by one. Let's start with the Atrevido core. Atrevido is a 64-bit out-of-order RISC-V core. It supports cache coherency with the CHI protocol, and it boots Linux. We support SB48. In this figure in the right, you can see the microarchitecture of Atrevido. It has all the components that you would expect from an out-of-order core. So how is this different from other cores? I think Filippo already mentioned this morning, Gazillion misses. This is the main differential point in our core. So Atrevido is designed to keep the vector and tensor units busy to achieve high vector unit utilization and high tensor unit utilization. The main limiting factor to achieve that is the memory wall, waiting for the memory to provide the data. Our Gazillion misses solves this by supporting hundreds, and yes, I said hundreds, of in-flight cache misses. So Atrevido can miss more than 100 times in the cache, and it does not stall. In different lines, there is no restriction. And this allows us to use the memory bandwidth efficiently. Let me illustrate the benefits of the Gazillion. In this graph, we have a benchmark that is traversing a vector, reading a vector multiple times in a loop. So we're reading a vector sequentially from the beginning to the end, multiple times in a loop. The x-axis shows the size of the vector. The y-axis shows the bandwidth that we get from the memory. And the green line is the memory bandwidth achieved by an Intel processor. And as we can see, when we increase the size of the vector, we observe several drops in memory bandwidth that correspond to the different levels of the memory hierarchy. If the vector fits in the L1 data cache, then the bandwidth is roughly 120 bytes per cycle. When we exceed the capacity of the L1 cache, we are bound by L2 cache bandwidth, which is a bit less of 50 bytes per cycle. When the size of the vector is larger than the L2 cache, then the reuse happens in the L3, which provides a bandwidth over 10 bytes per cycle. And finally, when the size of the vector is larger than the L3, we are bound by main memory bandwidth, getting 3.8 bytes per cycle. So how is this, how much better our Gazillion misses is compared to this? The red line shows the memory bandwidth achieved by the Atrevido core with the Gazillion misses. As we can see, the bandwidth is always 64 bytes per cycle. That is the bandwidth of the L1 cache, regardless of the size of the vector. So here's the trick. If the number of misses that we support is larger than the memory latency, and the application has many independent memory accesses, a lot of memory level parallelism, then we run at full speed. We never stall due to the memory. We also have developed a vector unit fully compliant with RBB 1.0. We do renaming of vector registers, and we support out-of-order execution of vector instructions. Regarding the data types, we support integer data types from 64 to 8 bits, and floating point data types from 64 to 16 bits. In terms of RBB, this means that our ELN equals 64. And we offer the 3 configurations that you can see in this table. VLN is the size of a vector register in bits, and DLN is how many bits are computed per cycle. And again, apart from the standard things that you would expect from a vector unit that fulfills the RISC-V profile, what other things we have implemented that are not in the original menu? Well, we have 3 custom extensions. The first one is the brain flow data type. This is very popular in machine learning. The second one are the FP8 convert instructions. This raised a lot of interest after DeepSeek. We had a lot of customers asking for these converts due to DeepSeek. And the third one is the allocation policy for vector loads. So the programmer can choose whether vector loads allocate a line in the L1 cache and in the L2 cache, or if they behave as non-allocate. This graph shows the overall microarchitecture of the vector unit. It consists of several lanes, and each lane contains a partition of the vector register file and an FMA. We also have a cross-lane network for instructions that require communicating data across the different lanes, such as reductions or gather instructions. And we have dedicated read and write ports in the vector register file for the load store unit that are used to execute vector loads and vector stores in parallel to the computations done by vector arithmetic instructions. And the vector unit receives the instructions from an issue queue, an out-of-order issue queue in the Atrevido core. We also developed a tensor unit to boost matrix multiplication in AI workloads. And we developed our custom matrix extension, because there isn't any ratified RISC-V matrix extension yet, although there are at least 3 task groups working on this right now. So maybe by the next year, we have 3 different standard matrix extensions. So our extension is based on the vector extension. We use vector registers to store the matrices. We didn't add any new storage or any new architecturally visible state. And we have 3 new instructions. One instruction to load a matrix from memory into multiple vector registers. Another instruction to store a matrix from vector registers into the memory. And a new matrix multiply instruction that operates on vector registers. And it performs this operation, A times B plus C, where A, B, and C are the matrices. In terms of RISC-V terminology, we are following the IME approach. This stands for Integrated Matrix Extension, which means matrices are in vector registers, no new architecturally visible state. And important, the data types that we support. You have them in the table. We support 4, 8, and 16-bit elements for the input matrices A and B, and we always accumulate in 32 bits. This figure shows the microarchitecture of the tensor unit. It contains multiple tensor cores, where each tensor cores perform a dot product operation. It has an array of parallel multipliers followed by a reduction tree. And its throughput is 1 dot product per cycle. We also have components to read the input matrices A, B, and C from the vector register file, and also to write the resulting C matrix back into the vector registers. And as I said, and I will repeat it again because we believe this is one of the strong points of our approach, we don't have new storage for the matrices. the vector and the tensor can access the same vector registers, which means that when we do some computation on the vector unit, and then next we want to do some computation on the tensor unit on this data, we don't have to do any memory transfers or any copy from vector registers to matrix registers. And finally, we have Cervell, our MPU that combines all our IP. It includes Atrevido with the Heraklion, plus the vector, plus the tensor. So what is the main idea? We believe that instead of having separate CPU, GPU, and TPU, each one with its own dedicated memory, we believe it's better to merge the three of them in what we call an all-in-one processing element. And in one of these all-in-one elements, core, vector, and tensor are tightly integrated. They share the first level cache. This results in better PPA because we avoid expensive memory transfers between CPU memory and GPU memory, or CPU memory and TPU memory. And it is also easier to program as it does not require explicit DMA transfers. Furthermore, we offer a unified software stack based on RISC-V. Instead of having C++ for the CPU, CUDA for the GPU, and a custom language for the TPU, we can program all the Cervell with just one language, C, C++, whatever. You compile it to RISC-V, and core, vector, and tensor run on the same ISA. And this is also one of the strong points. It is highly programmable to make it resilient to changes in future AI algorithms that for sure will happen. So in Cervell, we tightly integrated core, vector, and tensor. We only have one unified instruction stream that includes a scalar, vector, and tensor and matrix instructions. Of course, we use the Heraklion to hide the memory latency. And right now, these three configurations in the table are the ones that are ready to be shipped and are the ones that we are offering to our customers. And as you can see, the performance ranges from 1 TOP to 128 TOPS. Let's talk a bit about the software. How do you efficiently and easily deploy a machine learning model on Cervell? With the Aliado SDK. This SDK includes a RISC-V toolchain, an ONNX runtime optimized for our IP. We have implemented all the operators in ONNX, matrix multiplication, transposition, softmax, etc., etc., etc. So you can take your machine learning model, export it to ONNX, and you can run it efficiently on Cervell. We also provide a set of popular models already converted to ONNX. So we offer flexibility to our customers. If you want to build everything from scratch, be my guest. You can boot Linux, you have all the tools that you are used to it. C, C++, Python, you can write assembly code if you want. But if you just want to deploy your model, a model that you have trained with a minimum pain and minimum effort, you can just use our ONNX runtime to get it quickly deployed on Cervell. And that's all. Thank you very much for your attention.
Questions for our speaker?
Hello, thanks for your presentation. Do you have some numbers to share from application you run on your CPU, or is that confidential maybe?
Yes, you mean numbers about real benchmarks? Yeah. I I can share numbers of utilization. I can tell you, for example, for Llama, we achieve over 80% utilization in the tensor unit for the matrix multiply operation, right? For the fully connected layers. And then we saw that it's really important that you cannot ignore the activation functions. It's really important because, yeah, it's good to have the tensor for matrix multiplication, but sometimes this is 50, 60% of the thing. Then you have another important part that are the activation functions. And with the vector, with our vector unit, with the configuration, the V8 times 4, we are getting over 70, 80% of utilization for the different operators, activation functions in Llama. Apart from utilization, no, the only thing I can show is the performance. So what we get in real applications are between 70 and 80% of the numbers that you see here. Yeah.
Thanks. I have a quick question. Do you have the hardware designed for custom extensions, or it's just pure ISA extensions? I mean, do you have specific hardware for those?
We have a specific hardware for those.
Okay.
It's not just software based.
Yeah.
We have a specific hardware.
Yeah, guess so. Thanks.
Yeah.
Other questions for our speaker? Either from the room or from the remote attendees? I have one final question. Thank you for providing kind of an outline of what's coming up. I understand AI has become a major focus for the company.
It is.
It was not like that in the first generation of Adrevido, but right. I understand the company kind of follows a market instinct there. Right. Do you think that this reduced precision technology, do you think that this is mature enough in the technology that you are developing? We had a presentation yesterday about this alternative representation, deposits and such. I understand with AI it's more FP4, FP8, etc. So if you have to trade silicon area, it would go to this type of arithmetic?
Yes.
If you can say kind of an intuition for us to...
Good question. The answer is yes. I believe this is a very promising path because it's showing benefits in real applications. I mean, NVIDIA GPUs already support this. They have support for FP8, FP4. They have their own custom formats. And I believe this provides a lot of benefits. First, the main problem typically is the memory. With the smaller data types, you have smaller matrices. And right now, there is a lot of interest on formats where the exponent or there is a scaling factor that is shared across multiple elements. And this is what is called microscaling. And this is a lot of interest in the industry on microscaling formats where you have maybe a 4-bit data type, FP4. You cannot encode that much with 4 bits, right? You have sign bits and maybe just mantissa. But then the exponent is shared. You have every k elements where typically k is 32. These 32 elements will share the same exponent, right? And then it's really easy to do the math and cheap because when you multiply by the scale factor, you only have one exponent. So it's very easy to do multiplication with the normalized floating point number, right? So yeah, I believe this is a very good trade-off. We are getting a lot of demand for these very narrow data types, and we'll see by how much we can push the compression. There is another big thing also that is sparsity. We only support dense models right now, but as probably you know, NVIDIA supports sparsity or some forms of sparsity. And the trick is half of the weights of one of the matrices are going to be 0. They're going to be 0 following a structured pattern. You don't have any freedom to choose which weights are 0. But if you do so, you can quickly identify which weights are 0 and you avoid